Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
This video is going to go ahead and focus in on complex numbers and operations. Now, complex numbers are also known as imaginary numbers. Why imaginary numbers? Really, they're just placeholders for when we're trying to do elevated math. So we need to make sure that it's not necessarily meant for all math and things like that, but it does have a place and there is a reason why we go into it. So we're just going to gain a basic understanding of it. Here's what happens and why. When we're looking for, say, x squared equals 25, we happen to know that 5 times 5, or 5 squared, is 25. We also happen to know that negative 5 times negative 5 equals positive 25. So when I look at this, I know that my answer for x is either 5 or negative 5. However, what about x squared equals 36? Negative 36, sorry about that. Well, squared means times itself. If I do 6 times negative 6, I get negative 36, but they're not the same number. This isn't squaring. So I'd have to have both negatives, but now that makes positive. This is not possible using real numbers. But let's say you're working on some, really, really hard math in the future. Maybe you're a theoretical physics. And you need some kind of placeholder. Well, that's what they have done, is that complex numbers is actually just a placeholder. So really the way that we solve this is we square root both sides. X squared equals 25. So x equals plus or minus, because you always use a plus or minus when you do the square root property to both sides, the square root of 25, which is plus or minus 5. And over here, we have that x squared equals negative 36. So x equals plus or minus the square root of negative 36, which is not possible. It's a negative. You can't square root a negative. Ask your calculator. It'll tell you domain error. So what they've done is they've said, okay, let the square root of negative 1 equal I. That's all they're saying. Substitute I for the square root of negative 1. So now that means plus or minus the square root of 36 times the square root of negative 1, because 36 times negative 1 is negative 36. Now we can finally do our square root. The square root of 36 is 6. And this is being replaced with its placeholder of I. That's all an imaginary number is a placeholder for that negative underneath the square root. Okay, so anytime you see a negative under your radical, the first thing you do is you pull out your eyes. Please not literally. That's kind of a tongue-in-cheek thing, but so in your final answer, complex numbers come in the following form. A is your real part. B is your imaginary or complex coefficient. Okay? You will also know that there's not an exponent on the I. Complex numbers do not have exponents on their I. So what happens if you get higher numbers, right? Higher powers. Well, let's think about this. If I equals this, which is what we said we were going to let it be, what would happen if I were to square the left side? I'd have to square the right side. So that would just be -1. So we had I squared reduced to -1. Okay. So I cubed, wouldn't that be I squared times I? So -1 times I would be -I. Okay. I to the 4th, I squared times I squared. -1 times -1, isn't that +1? I to the 5th is going to be I to the 4th times I, which is going to be 1 times I, which is just I. I to the 6th is I to the 4th times I to the 2nd. 1 times -1, that's -1. I to the 7th is I to the 4th times I to the 3rd. That'd be 1 times -I, that's -I. So that means I to the 8th would be here, I to the 9th, I to the 10th, I to the 11th, so on and so forth. So we have a pattern. I won, yay, I won, right? Negatives in the middle. And now we can just think. Let's say I wanted to do I to the 23rd power. Okay, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Boom. -I. You can always do that. That pattern will hold true. However, if we get really big numbers, maybe we don't want to count that high. So there's got to be another way. Let's say you want to do I to the 123rd. Okay, well, it's odd. So that means it's either going to be I or -I, because if you notice that I won pattern, the odds had the I's, the evens had the positive and -1. However, we know that this is I to the 122nd times I. And if I divide this by 2, that would be 61. Now I can substitute -1 in for I squared. So if I have 61 negatives, it would be negative. So that is your proper way to do I to any power. You could sit there and count. Evens are going to be 1 or -1. And sometimes it helps to think of them in quantities of 4. So anything that's divisible by 4 would be in that last column. So this column would be exponents divisible by 4. Like I to the 4th, I to the 8th, I to the 12th. All of these three all equal 1. So if that helps, that's great. So let's go ahead and let's look at reducing some radicals that are not technically real. So we'll do -72. So step 1 in doing this is you have to switch this to a positive number times. So really, now if you've forgotten, you might have the square root of 72 is not a small number, and so we need to reduce it just like we would reduce fractions. There's a historical reason, and it has to do with they used to have charts with different radicals in them, and 72 was just a really big number, and a lot of them only had prime numbers, so we can always reduce this down. There is a very formal way, but you have to know your perfect squares. Not everybody does. So step one, I'm going to say, let's just do your prime factorization. We knew 72 is 8 times 9. 8 is 4 times 2. 9 is 3 times 3. And that is also 2 times 2. And I say we fold socks. That's what I call it. Okay, so we're looking for pairs because there's an assumed index of 2, because we're undoing a power of 2. So I think about it like folding socks. You have just taken out your socks from the laundry room, from the dryer, and the square root symbol, the radical, is your basket. And you're going to fold pairs of socks. So, hey, here's a matching pair of socks. We're going to fold them together, roll them up in a ball, put them away. Here's a pair of socks. We're going to fold them together, roll up in a ball, put them away. Now, somehow the dryer eats socks. I don't know how. It just seems to happen. 2 times 3 is 6. And we still have one sock waiting for its partner underneath. And just to show you and remind you that they are indeed equivalent, we are getting the same decimal. So no rounding, we have reduced radical, and we took care of our imaginary number. So before we can do anything with this problem, we really should go ahead and, well, you have to take care of your negatives first. You cannot work with your radicals until the negative has been taken care of. So we're going to change this to 20, and I'm just going to go ahead and write the I at the end, instead of doing the step where we write the square root of -1 and then write the I. So step 1, pull out the I's. And then why do I have 2 different baskets of socks? Can't I just throw them all into one? Absolutely. Okay, I just dumped all the socks into one basket. Now, could I multiply this together and get 300? Yes, I could. But I'm going to prime factorize this so I can fold socks. So 20 is 4 times 5, which is 2 times 2. 15 is 3 times 5. So we have a 2, a 2, a 3, a 5, a 5. And instead of writing I squared, or II, I'm going to write I squared. And of course, these are products, right? Okay, we're going to fold the socks, put them away, see if the dryer left had leftovers. A pair of 2s, a pair of 5s. Remember, we're putting them away, rolling them in a ball into one pair and putting them away. A pair of 2s, a pair of 5s. So 2 times 5 is 10. We have 3 left over, and I squared is -1. So -10 root 3. By the way, if they ever change this number, this index, it just changes your group size. Maybe if it's a 4 out here, you're finding socks for your dog. Okay? Whatever friendly animal you have, how many ever legs it has, this tells you how many socks you need per group. All right, so all you have to do when you're given it and you're reducing it is to pull the negatives out first and write a I, then reduce your radicals. Well, what about just basic algebra with these complex numbers? What might that look like? Well, we can add them. 7 plus 3i plus 5 minus 8i. In this particular problem, the plus really doesn't mean anything, or not the plus, the parentheses. We just have 7 plus 3i, and we're adding 5 minus 8i. Notice how I lined them up. Some people like to go ahead and write it vertically instead of horizontally. All right, so we're going to add 7 plus 5 is 12. 3i plus negative 8i is minus 5i. This is our answer right here. It's written in a plus bi form. Our a is 12, our b is negative 5. Okay, new problem. 6 minus 9i minus 17 plus 3i. Oh, blurry. There we go. So in this case, just like if this were a variable or an x value and we had to simplify it, we're going to distribute the negative. 6 minus 9i minus 17 minus 3i, and then combine like terms. So 6 and minus 17 smashed together to make negative 11. Negative 9i and negative 3i smashed together to make negative 12i. So when you're adding and subtracting, these work really just like having like terms. Honestly, that's all we're doing is combining like terms. So what about multiplying? Okay, 4 plus 3i times 6 minus I. Well, this looks like a FOIL problem. Some of you are very good at visual FOIL. For those of you who aren't, I'm at least going to make it like a Punnett square-ish. I'm just not going to draw the grid right now. 6 times 4 is 24. 4 times negative I is negative 4i. 3i times 6 is 18i. And 3i times negative I is negative 3i squared. And if you were to FOIL this out long way, you'd get the same thing. So we can see some like terms. We're going to have the 24 minus 4i plus 18i minus 3, but I squared is equal to negative 1. Remember, when we answer, we don't want an exponent in our final answer, so we replace that as quick as possible. So we'd have this is a constant here, and this is a constant here. And if I do that math, I get 24 plus 3. That's 27. And negative 4i plus 18i is positive 14i. So the only difference between this and a FOIL problem is that you have that extra step of changing that negative 1 in for I squared. Okay, so 6 plus 5i times 6 minus 5i. You might notice that these are very similar to each other. One's a plus and one's a minus. You might have seen that pattern as a result to an answer in a factoring problem, but we'll just go ahead and this time I'm going to multiply horizontally. 36 minus 30i plus 30i minus 25i squared. 36 minus 25 times negative 1, because if I look at these, those cancel out. And if I were to type this problem into my calculator, I would find out that it equals 61. Well, that is a simple answer. The reason why we got a pretty nice rational answer is because these are something known as complex conjugates. Complex meaning they have the I, conjugates meaning one's a plus, one's a minus. A plus bi and a minus bi. Anytime you multiply your complex conjugates, you will get a rational product, which is going to be very helpful to us because we don't actually divide imaginary or complex numbers. So we did the adding, subtracting, multiplying, but we don't actually divide these. So you might see something like 3 minus I divided by 6 plus 5i. And you might say, hey, I thought you just said we don't divide them. We don't, but we still write them in a plus bi form. So we have to have a way of getting to a plus bi form. And that means we need a rational number on the bottom, which means we need to rationalize our denominator. And to do that, you're going to use your complex conjugate. Well, what was our complex conjugate for 6 plus 5i? Well, if you have the plus, then your conjugate's going to be the minus. And we've all worked with fractions before. If you multiply the denominator by something, you must multiply the numerator by the exact same thing. So our numerator is going to multiply out to be 18 minus 15i minus 6i plus 5i squared. Our denominator, 6 plus 5i, 6 minus 5i. We just did that, right? 61. Okay, let's simplify that numerator now. 5i squared, we know 5 times i squared is 5 times negative 1, which is negative 5. So 18 plus negative 5 is 13. Negative 15i and negative 6i is negative 21i. And our denominator is 61. So that's really not a plus bi form until we do this. 13/61 minus 21/61 I. Now it's written as a plus bi form, where a and b are ratios or fractions. Working with quadratics, you've probably already been looking at solving things like x squared minus 49 equals 0. And you could have solved this through factoring. You would have factored and got x plus 7, x minus 7. Then you would have done your zero product property, x equals negative 7 or x equals positive 7, because setting each of these parentheses equal to 0. When there's not a b value, factoring is not necessarily our fastest mode. Instead, utilizing our square root property is, so we're going to add the 49 to both sides, and then we're going to take the square root of both sides. However, when you square root a number, don't forget the plus or minus. So x will equal positive or negative 7, which is the same thing we got there. This works, the square root property is best when your b value of your quadratic equals 0. So that's when that's best. So what about if we had x squared plus 25 equals 0? So now if you tried to factor it using real numbers, we couldn't actually do that. So we'll subtract the 25 to the other side. Do the square root of both sides. Notice how I put that plus or minus there. And there's that negative. So we have to pull out the negative by utilizing the I, and then we get plus or minus 5i, which the state of Missouri wants us to be able to factor this as x plus 5i, x minus 5i, and we can see how the square root property reflects that as well. So keep in mind, I is just a placeholder for this value. That way you can do advanced math. If that happens to show up, you don't have to put a stop on your math. You can continue and try to go through the theoretical math to see if you can't come up with something new for the real world. So,
thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.